something like, I don't know, how about e to the ax? What are you guys going to look like? You guys can change my variable. I like T's instead. Sorry. How about Laplace? 1 over s minus a, as long as s is bigger than a. I think if I were to Laplace, I shouldn't be asking you guys these questions. Maybe you don't remember. Let me just give them to you. If I were to Laplace something like the sine of, you guys didn't like these, did you? I think I simply get an a over s squared plus s squared. However, if I were to Laplace the cosine of at, I think that's going to generate an s over s squared plus a squared. And you guys, I really don't remember what happened yesterday in class. I think I opened my book. I said, well, jeepers, your author derived one of these two, and I derived the other one, so that you've got both derivations. If you were to Laplace t to the n, you might not remember this, but what you get is n factorial all over s plus. Well, I misspoke, sorry. I meant. Anybody? Yeah.
S plus 1.
S over
n plus 1.
Power.
Yep.
I think if I were to Laplace the derivative function, it's going to give me this. S times Laplace of y minus y valued 0. You guys, at the end of class, I derived this. I just didn't use it for anything. I'll use it right now in solving a PE. I also maintain that if I were to Laplace y double prime, what I end up generating is s squared times Laplace of y. Anybody? S times.
Minus s times y of 0 minus y prime of 0.
Oops, sorry, I meant y prime. And I think this is enough machinery for you to start solving DEs. Can I cover all the sections? Can I jump around a little bit?
What's the shift?
Oh, the shifting theorem is extremely important.
Yeah.
On the final exam, I don't even think you should expect to solve a DE with Laplace transforms without the shifting theorems being applied. But let me take some smaller baby steps today.
Okay.
And you guys, can I do this? Can I jump around a little bit? If I were to be like the author of text, the first 3 or 4 sections would be theoretical. I never really get to solve DEs yet. I promise I'll cover everything, but can I just jump ahead since we already have the tools now to solve DEs and dive in and solve one? So here's an example I can tackle. And you guys, I don't want to flub up, so I've got some examples I made up. How about something like y double prime plus 4y being equal to 166, with y evaluated at 0 being equal to 3, and y prime evaluated at 0 being equal to 6. And I maintain what I have in the list over here is going to be sufficient enough for me to solve these DEs. So here I go. I think if I were to Laplace each sign, I don't know getting this. You guys, this is the first example I'm giving you. So I'm writing way too much. So my subsequent examples, I'll be skipping a few of these steps. Chris?
Is it 166?
It is.
It's a big number.
I know, I must have it there for a reason. So if I Laplace the left-hand side, I'll have to Laplace the right-hand side. But you guys, the Laplace transform is indeed a linear transformation. It has all the linearity properties. So I think on the left-hand side, what I really have sitting in front of me is Laplace of y double prime plus 4 times Laplace of y. Being equal to the Laplace of that constant, but jeepers, the Laplace of the constant over here is
1 over 166.
Isn't it?
I don't think it is. Sorry. It doesn't say.
See, I think it does say.
It's 166 over this.
Because I think if n is equal to 0, that's just 1. Laplace of 1 is going to be 1 over s. So I think it does say that.
I was looking at the first one, setting a equal to 0, and then it'll be linear.
Oh, you know what? That's how I said it in class as well. You're right. 2 different ways of looking at it. And I think I've got my 166 times my 1 over s.
66.
It's not 666. And everybody, check out how with the very first term, if I use that very last identity down there, it's going to tell me I can replace Laplace of y double prime as an s squared Laplace of y minus s times y of 0 minus my y prime is 0, plus my 4 times Laplace of y, bless you, being equal to 166 over s. And I do have some initial value conditions I can plug in. So plugging 3 and 6, is that 6? And for y of 0 and y prime of 0, I have the following. My s squared times the Laplace of y minus s times y value of 0, because that's just a 3s, minus y prime of 0 is 6. Now, if I were to isolate the Laplaces of y on the left-hand side of the equal sign, I think it's going to give me an s squared plus 4 times the Laplace of y being equal to, I have no idea what. Is that a 166 over s? I don't know what the rest is. Is that a plus 3s plus 6? Shoot, you guys, can you appreciate how this is just transformed into a math D question? It's just an algebraic question, equation in the Laplace of y. I'll isolate it. And I see the Laplace of y is nothing more than 166 over the product of these two beasts. Plus the 3s over s squared plus 4. Plus is 6 over s squared plus 4. Now I want a yes or no answer. Do you think to inverse Laplace of 6 over s squared plus 4 is going to be easy?
Yes.
Yeah, I think it is, because if I had sitting in front of me a 2 over s squared plus 4, inverse Laplace is just going to give me a sine function. And if I shave out factor 3, that's exactly what I have. I think using the same logic with the preceding term, if I shave off factor 3, then jeepers, notice how this is the Laplace of a cosine. So inverse Laplace gives me a cosine right back. Oh, you guys, shoot, I goofed up. I can't see how to inverse Laplace, so I will commit to partial fraction decomposition. And I'll separate that into a couple fractions. So I guess I need a piece of scratch paper. So pulling out my nifty little piece of scratch paper, I'm going to take a peek at that 166 over s times s squared plus 4, and I'll separate this to an a over s, plus how about a bs plus c, all over an s squared plus 4. Getting rid of fractions, I can easily have the 166 be equal to a times s squared plus 4 plus bs plus c times s. And if I allow s to be equal to 0, let's see what happens. I don't know what happens. Does that give me a... I have no idea why I put a 166 there. Does that give me that a is equal to... Is that 83 halves?
I don't see why you couldn't have just factored out the 166
And do what? Oh, just not deal with it?
Yeah.
That's fine, you're just going to bring it back in the end. You're right, I guess so. And if I already equate the coefficients of maybe my s squareds, doesn't it tell me that a plus b is equal to my 166? So that my b is equal to... I can't do it. Is that going to give me a 9? A 4? A 2? Over 2? Yes, sir.
If we're doing s squared, shouldn't it be a plus b equals 0, because there's no...
I'm so sorry. That makes my life so much easier. If I'm going to equate my s squared coefficients on the left-hand side, that's just a constant. I really should have a 0. My mistake. So making my life a little bit easier. And lastly, maybe equate constant terms.
Coefficient of s.
Yeah, equate constant terms is just going to give me a right back. So I think the only thing left I could do is equate coefficients for s. I think that gives me a 0 being equal to, oh shoot, is it that easy?
C.
Just my c. I guess we're done. And let me slap everything in. That leaves me with the sum of these two fractions. Namely my a, which is 83 over 2 over my s, plus my b, which is negative 83 halves, times my s over s squared plus 4. And finally, inverse Laplacing. that tells me that my final solution, my function for y in terms of t, is gonna be, look at that. That's just gonna give me my,
83 halves.
a constant. I think right here gives me a minus 83 over 2 times the cosine of 2 times t, plus my 3 times my, and then my, and of course, you guys, before I wrote down my solution, I could have combined a couple of these terms. Before or after doesn't make any difference. I have to confess afterwards there are a couple of terms I can combine, namely the second and the third, and so I think finally my y of t is my solution to the dE is that constant. Plus, I have no idea what, is that a minus 77 halves cosine 2t if my arithmetic's okay? And then finally plus my 3 sine 2t. Now you guys step back for a minute and look at the beauty behind this approach. I Laplace both sides. Once I Laplace both sides, there is no calculus. There may be calculus to derive or being used to derive that Laplace of certain things are what they are, because Laplace is defined in terms of an improper integral. But you got to admit that's pretty slick stuff, Chris.
That doesn't look anything like what you would get if you tried a complex value solution method. Or rather, I'm sorry, no, it's sine and cosine.
I disagree completely because I think with the complementary solution, notice that my characteristic equation is r squared plus 2 equals 0. Sorry, r squared plus 4 is equal to 0. There's where my cosine and sine 2t terms come from. And Chris, check this out. That's a constant. So I think my trial particular solution should be some constant. Oh shoot, look at that. It is. I think it matches in my mind what I would traditionally do anyways with the method of indeterminate coefficients. So you see it.
Did you inverse Laplace of first term 83 over 2s by looking at the Laplace of t to the n, where
I
it
did.
is 0?
I did. And in fact, if you want to put that as an additional Laplace transform, just put it in. Laplace of 1 is going to be 1 over s. And it's a special case of what you just said.
It looks like Laplace is kind of limited in the way that method of undetermined coefficients is.
Ah.
'Cause it only.
It very much is so because of what I can Laplace over there. But the nice thing about this, in electronics, a lot of times what happens is I get these split domain functions. I charge a capacitor and then I run with it. And when it comes to these piecewise defined functions, to Laplace them is really, really easy. So right now, as of today, it looks extremely limited, just like it was back with method of determinate coefficients. But you and I are really going to broaden our horizons. Maybe, well, I don't think today. I don't think much time. But tomorrow, definitely.
Is there like a variation of parameters for Laplace?
No, but there are ways of doing this. I'm going to have a function, a switch, in a circuit that has no electricity applied yet. But after a certain amount of time, I flip the switch on. And electricity is going to be variable. And then I flip the switch off again. I can use those kinds of functions in the forcing function's position and still use Laplace transform. And since that happens so often in electronics, they're nice tools to use. For the circuits class we have on this campus. Now I've heard in circuits, the course right now, the way it's being run, they don't use Laplace transforms, but you can use them all over the place. It's so wonderful as an application.
So do they require you to have the initial values because we have them in our Laplace? Like, do they only work for ones that have initial values?
I can't say that's all they work for because, what you could do is keep this as a y prime is 0 and y is 0. It's just that you got these lingering coefficients at the end. It's fine. It works. It just looks kind of funky. And so I think traditionally we'd like to actually have those initial value conditions, but it's not necessary. You guys, do you think I can erase this and just try it again? So, another example. Oh, let's see if I have something more interesting. How about something like a y double prime minus 3y prime plus 2y being equal to 12e to the 4t with these initial value conditions. Here too, you guys, it does look like a traditional DE I would have using the method of undetermined coefficients. Let's give it a shot. I think if I Laplace the left-hand side, I'm simply left with the Laplace of y double prime minus 3 times the Laplace of single y prime plus 2 times the Laplace of y. Being equal to 12 times the Laplace of e to the 4t, but the Laplace of e to the 4t is s minus that coefficient a. And on the left-hand side, I can, with those last two statements over there on the right side board, I can just ding on the first two terms and transform into expressions, no pun intended, the word transform, into expressions involving the Laplace of y. And I think I get this. I get s squared times the Laplace of y. Is that a minus of
S of
y of 0? Minus y prime of 0 being minus 3 times the Laplace. Well, I misspoke, everybody. Sorry. I meant minus 3s times the Laplace of 1. Is that a plus 3 times y of 0? Plus 2 times the Laplace of y being equal to nasty business. Now diving in and substituting where appropriate, I guess it's minus sy of 0 is going to be minus just an s. This minus y prime of 0 is going to be minus 0. And finally, this plus 3y of 0 is going to be is that a positive 3? Oh shoot, I skipped some steps. I skipped these 3 terms. So combining them into a single term, I'll factor out the Laplace of y, and I think what I have left over is nothing more than s squared minus 3s plus 2. You guys notice how those coefficients become a quadratic expression in s for which I'm going to divide both sides, for which I will involve that partial fraction decomposition prior to inverse Laplacing both sides. First things first, let me bring these two b's to the right hand side of the equal sign. And I think that tells me that the Laplace of y is equal to my, is that an s minus 3? Over s squared, I can't read it. Is it minus 3s plus 2? Plus my 12 over s squared minus 3s plus 2 times s plus 4. Oh, it's like, actually it's minus 4, excuse me. You guys, I don't know what to do next. I'm being honest. What do you want to do next? As is, or you want to
PDF.
weigh it?
Well, why don't you factor that? Because it's just going to be an s minus 2 and s plus 1. So.
Yeah, I know, but I was kind of hoping you guys would say this. Since I got a partial fraction decomposition, the first fraction as well as the second, they already have something in common in terms of my denominator. Wouldn't in this example it would be nicer just to rewrite everything on the right-hand side of the single fraction? So I only have to commit to partial fraction decomposition once. And if I were to do that, I see that the Laplace of y is equal to some fraction whose denominator is kind of nice. Is that an s minus 1, s minus 2, and s minus 4? Whose numerator is that an s squared? Is that minus 7s? Is that a plus 24? Michael?
Would you multiply the top in order to combine?
I really did this. With my red pen, I merely multiplied top and bottom of the first fraction by an s minus 4. And then pulling out my nifty piece of scratch paper, if you guys are okay with this. I see that my s squared minus 7s plus my 24 all over stuff is equal to my a over s minus 1 plus my b over s minus 2 plus my c over s minus 4. And ridding myself of fractions, that leaves me with my trinomial upstairs being equal to this mess. But you guys, there are no quadratic factors. This really is gonna be 100% piece of cake. When I substitute in for S, my 1, or my 2, or my 4. No issues whatsoever. I just need to crank out the arithmetic. And arithmetically speaking, if S is equal to 1, these two terms drop out. On the right-hand side, I'm left with, I said S is equal to 1. I'm left with a 3a on the right-hand side. Sorry, so slow. On the left-hand side, I'm left with a, is that an 18? So a is equal to 1/6. If S is equal to 2 on the right-hand side of the equal sign, the
What?
first and last group is dropped.
Wait, that doesn't make any sense. How did you do that?
It's just 6.
Isn't it just 6?
No, you turn yourself upside down. It's perfectly fine.
Oh, okay.
And I think if S is equal to 2, the first and third groupings on the right-hand side drop out, but in the middle term, is that going to give me a 2 times negative, it's going to be a 1 times negative 2, it's going to be a negative 2b. On the right-hand side, however, jeepers, what do I get?
14.
Yes, I get a 14. Which means b is going to be a negative 7. And finally, S being equal to 4 drops out the first and second groupings on the right-hand side. But that leaves me with a 3 times 2, which is 6c, being equal to is that 12? So C is equal to 2. Ah, shoot, that is really nice. So 6, negative 7, 2. I said 6, negative 7, and 2, all over my S minus 1, S minus 2, and S minus 4. So when I do indeed inverse Laplace both sides, my final solution is going to be nothing more than
6 e to the negative,
You could take
6 to the negative t.
minus 7.
e to the
2t.
Got it.
Plus 2.
Very nice. I'm happy. Are you happy?
Question,
Yes.
do you care what we do on tests? With regards to method,
What are you referring to specifically?
whether we cross something or use the method?
Oh, I see your point. You should expect me on the final exam to be really, really picky and maybe to be directive. Only because on the final exam, if I want to see you use Laplace transforms, I want to see that you can use some sophisticated ones involving some of what I call the shifting theorems. And so, yeah, I can see myself on a final exam twisting your arm to using one technique over another. Mike?
For getting, I guess, y and t, what was the relationship between, I guess, when you inverse Laplace? Like, is it just you take whatever's on top and move it to, like, a coefficient?
You know, I really did do that. You know, technically speaking, I was really thinking the first term is 6 times this.
Okay.
Now take a peek at the following. Notice how 1 over s minus 1 is already understood to be the Laplace of e to the t, replacing a with a 1. So when I inverse Laplace, I got the e to the t right back. But you guys, this whole business of my inverse Laplace, you know, technically speaking, it's really illegal. I may have proven to you that the Laplace transform is a linear transformation. I never showed you that it has an inverse transformation. I just wanted to say to cut to the chase and actually use these to solve DEs. Bottom line is that if a function has what we refer to as exponential order, then with this Laplace transform, I will be able to inverse Laplace. And exponential order simply means this. Neglecting some coefficients out front, there's some exponential function that bounds above your particular function, whatever that forcing function is. But I'll get into that theory. I think what I want to do next, however, is really build on the list over here. And to build this list, I want to talk about that first shifting theorem. So here's the first shifting theorem. Basically, it says following. If I'm going to Laplace some function f, a function in time t as a variable. Oh, but shoot, it's got a coefficient. put e to the at. I end up getting nothing more than the Laplace of little f, which I'll call big F. You got it, actually s minus a. In other words, Laplacing a function with a coefficient as such, a non-constant coefficient as such, ends up shifting the corresponding Laplace transform. Hence the title shifting here. Of course, you guys, I don't want to come to class and just say things out of thin air. So do you mind? Can I take some time to prove this? First things first. Laplace of some function little f, you've got a t. If it does exist, I sometimes will refer to it as correspondingly uppercase big F, you've got it, shoot the function, the variable, S. Where? Keep in mind, the Laplace of that function little f, you've got a t, is really by definition the evaluation of this improper interval. You guys, I don't like the way I wrote that. Can I change it a little bit? So watch me with my green pen. I just erased that, which corresponds to sitting right there with the coefficient. Keep that in mind. So if you guys don't mind, I think at this point I'm going to dive in and I'm going to prove the first shifting here. It is an absolute piece of cake. It's almost obvious, as long as you see that. So if I were to Laplace e to the at times some function f in terms of t, I think by definition of Laplace transform, I simply get this, the improper integral of my e to the negative st times e to the at times f of t, and I'm integrating respect to t. But don't you guys think this is the improper integral from 0 on up of e to the negative do you mind? Times f t dt. But like I said, this coefficient of t is going to correspond to exactly what the Laplace is going to be in terms of. And so I think I end up getting the Laplace function evaluated at that particular coefficient of, whoa, hold it, I forgot my t. That's just a coefficient. I get my s of f of s minus a. I'll proclaim my happiness. So you guys, maybe not solving the e yet, but just messing with Laplacing with these shifts. What can you say about the following? So it's big F of s minus 2. But big F corresponds to the Laplace of what function?
T squared.
Thank you. What's the Laplace of t squared? 2 over t cubed. 2 over s cubed. Chris?
So you got rid of an entire function by shifting
Yeah,
Laplace.
I know.
What? How does it even happen?
You gotta admit, that is a proof. That is a proof. I proved to you that it has to happen.
Yeah, it just,
It may not be intuitive, but it's definitely a true statement. But humor me. You guys, I forgot where I'm at. I've lost it. Sorry. What's the Laplace of even 2t?
Over there, it's 2 factorial. It's 2 is cubed.
The Laplace of e to the 2t?
we don't care.
One
Good.
over.
It's irrelevant. What's relevant is the Laplace of t squared, which is 2 over s cubed. It's just that when I write the 2 over s cubed, I will shift it over 2 units to the right.
S cubed.
That's what I said. Just for my sake, whatever.
S cubed.
Say that again.
Just S.
But I thought I had a shifting. Because I think
Oh,
this factor right here
shifting.
corresponds to a shift in the direction of 2 units to the right. That corresponds to
Okay.
What if I asked you to Laplace, how about e to the negative t times the cosine of 3t? What are you going to give me? Oh, you guys are killing me.
S minus, or S plus 1.
Or s minus negative 1, all over,
S plus 1 squared.
yeah,
Plus
plus what?
1.
I can't hear you.
3.
I can't hear you.
9.
Do you see how when I inverse Laplace, I'll be completing the square all over the place?
Oh, yeah.
What do you think you could say about Laplace? Is this an application of the shifting theorem? Yeah, it is. If you consider the function 1 as being multiplied, that's my f of t. What's the inverse Laplace of 1? 1 over s. It's just that I got a shift of 3 units to the right. Ah, shoot, you know what I just did? I just misguided you. We didn't have to use the shifting theorem here, did we? If I had the 1 to Laplace e to the 3t, look at the very first line. Don't I get just 1 over s minus 3? I'm being silly. I'm just saying I could have used the first shifting theorem. Chris?
So why is the Laplace transform defined this way instead of some other way?
You know what? That's a really good question, but I have to confess, I have no idea what's going on when Laplace, historically speaking, was working in his potential theory. I really don't know what he was working on. And so I don't know how this is pertinent to that theory. All I know is that I can use these to solve differential equations. I just never come across it. I've never looked for it.
It seems like we're just using something very arbitrary, so aren't there other transformations that could
You know what? You're right, but this particular topic is not unique for that. Whereas somebody just fell upon the fact that he or she can use this to do what he or she wants to do, which is solve differential equations. Certainly, the development of Laplace transforms was not devoted to solving DEs. So it's more of a happenstance that somebody just fell upon and said, "Wow, this is really cool stuff. I can use this to easily solve differential equations."
But in that case, aren't there potentially other transformations that, or is this an entire field of unfair right now?
That was very putty, by the way.
I don't see how it's funny.
There are a lot of other specialized techniques, particularly when a differential equation is of a very special form. But this is much more broad. This is much more general. Okay?
Is it special because it's a transform that can transform a derivative of a function into something done?
Oh, that's only one of the reasons. I also think it's special because Laplace in the basic functions is so clean, for which I could use partial fraction decomposition to undo everything. I just think for a lot of reasons, this is really smooth. And you have to confess, once the Laplace both sides, it really is a math D game. I mean, it's all algebra, no calculus. It's just that it's very calculus based. Am I proving to you that Laplace transforms do what they do, and in deriving those individual Laplace transforms?
So in that last example, where you're using the shift theorem for e to the 3t,
Yeah.
wouldn't it be 1 over s times s minus 3 because the Laplace of e to the 3t is s minus 3, but the Laplace of 1 is 1 over s?
See, I disagree. I don't think there's any multiplication there. I think it's composition. Because I think what this should be is the Laplace of some function little f, I'll call it big F, e divided s minus a. Where? If I were to Laplace 1, it really gives me my big F of s. It's just that means my big F of s is going to be the Laplace of 1 over there is just a 1 over s. So I think I'm taking this big F function in terms of s, and I'm replacing the input s with the s minus 3. There's no multiplication. It's functional composition.
So you're just substituting in,
The s minus 3 for the s.
you're substituting in the Laplace of one thing into the form of the other Laplace.
I agree. Or how about this, putting on some special glasses? Once I Laplace, I don't see an exponential factor anymore. I just know that whenever I see an s, I shift to the right 3 units. Thank goodness this is true, because if you were right, if it really were 1 over s times s minus 3, I'm in big trouble, because I think we already know the Laplace of e to the 3t is just that.
Yeah.
Thank goodness. My world, my universe is all the time. Has anybody else attacked me? Michael?
In terms of, I guess, your proof where it's like that big F and then S minus A.
Yes.
When we're looking at our composition of the Laplace transform, which one is S and which is A? Or
Okay,
is it not?
always. This factor right here, the exponential factor with the first shifting theorem, will always be the actual shift. It's really what's being multiplied to it that's going to generate the actual Laplace transform. That's always going to be true with the first shifting theorem. I'll mess it all up in a second.
So the big F just represents Laplace transform, is that?
Yes, the big F is Laplace transform corresponding to the little f. In this case, my little f is a constant function.
And then what Michael just said, or what you just answered, was that the first part of that multiplication is going to be big enough.
No, I think the first thing circled, the exponential factor, I should say, corresponds to the actual shift. Whereas the function being multiplied to the exponential factor is really what's going to give you the actual Laplace transform. And you have to confess, look over here, I know I didn't explicitly write it, but if you allow n to be 0, or you allow a to be 0, either one, I think either one says the Laplace of 1 is simply 1 over s.
Right.
So that 1 over s really is my big F, because that is the Laplace of that second factor that I labeled as 1. So do you think I can set you off with a bit of practice?
Sure.
So jump back to section 8.1, do some really simple questions.
You already assigned this.
Oh, did I really?
Yeah.
Don't listen to me then.
Oh, you did yesterday.
I don't remember. I thought I pushed everything off for today. So you guys in this section, the homework tonight, we're just actually diving in and solving some DEs, just like I did for the class.